Let's analyze and solve the majority element coding problem. We are given a zero-base array of integers called nums. The array is unsorted, and we have to find a majority element, which is defined as an element that appears in that array more than half of the times. So, in other words, if our array size is n, so we have n integers, we have to find an element that appears in that array n divided by 2, to be more specific, a floor, times. And the description of that problem says that we are guaranteed that such element will always exist in the input data. From the point of view of coding, we have to write a function, let's call it majority element. The function will get our nums array as an input, and we are supposed to return the majority element. We are also given a set of constraints. The most interesting part of that constraints is that array is never empty. And there is additional challenge in this problem. We are being asked to develop an algorithm that works in O of n time, in linear time, and also in constant space, so O of 1 space. And that's pretty much the entire problem. To solve that problem, we can start from the brute force approach, and I will use the array from example 2 to show how that works. In this array, we can notice that the size is 7, so n equals 7. The majority element will be an element that appears more than our threshold, that is equal n divided by 2, which is 7 divided by 2, which is 3. So we are looking for element that appears more than 3 times. And we can do it as follows. We will have a for loop that will start from the first element, and we will be going to each and every element of that array. And for each element, we will have another for loop, and this for loop will again start from the beginning, and it will go through all the elements and count how many times the element in that outer for loop appears in that array. So in this example, our outer for loop points to 2. So the current element is equal to, so let's write it. Current equals 2. Count equals 0. And we will start the inner for loop, the blue one, and we will start counting how many times we can see 2 in the entire array. So we will start from 0, there is a 2, so 1. We will move to the right, there is another 2, so our counter is now 2. We will move to the right, it's 1, so the counter is not going to be incremented. Same for this element, it's another 1, it's another 1. We found another 2, so our count is now 3. And we are at the threshold, so it's not yet a majority element. And we will move to the last element in this array, and it's again 2, so the counter is 3. And after each increment of the counter, we are checking whether the count is greater than the threshold, and if it is, then we will return that element. And that's very easy and straightforward algorithm. The downside of this algorithm is that the time complexity is O of n squared, because we have 2 for loop, and for each element in the outer for loop, we have to process the entire array to count how many times that element pointed by the outer for loop appears in the array. But the space complexity is just O of 1, so it's good. We are not using any extra memory. And that's the idea for how to solve it using a brute force. The brute force solution works, but the time complexity is not great. So we can find a better solution. One of the approaches is to use hash map. And before I show how that works, let me modify this array a little bit. So I'll swap the element with the index 6 with the element with the index 3, which will be beneficial to our explanation. So here goes 2 and here goes 1. And as I said, we will use a hash map. So this is our hash map. The value will be a count. or counter, and the key will be a number itself, which is the value inside our array. And we will have a for loop, which we will use to process the entire array. And we will be counting how many times every element appears in the array. And as we go, we will be also checking if the counter is above our threshold, which is 3 for this array. So let's show how it works. We are at the first element in the array. The element is 2. 2 is not in the map, so we will add this to our hash map with the value with the counter 1. Then we will move to the next element. It's again 2, so we will increment the counter, and the counter is now 2. We will move to the next element. It's 1, it's not in our hash map yet, so we are going to add this one with the value for the counter 1. We will find another 2 here, and we will increment the counter for the 2, which is now 3, which is exactly our threshold. And we will move to the right. It's 1, so we are going to increment the counter of 1s from 1 to 2. And we will move again. We will find another 2. We will increment the counter, so now it is 4. And because we've reached the value of the counter for the number 2, that is above our threshold 3, we will immediately return 2 as a majority element. And this algorithm has a better time complexity than the brute force one, because we just process the array once, so our time complexity will be O of n, where n is the size of the array. But the space complexity got worse. Space complexity is now also O of n, because we are storing the values in the map. And that's how we can solve the problem using a hash map. Another way to solve that problem is to sort the array. The downside is that we are modifying the input array, but if we can do that, if the problem allows for it, it's a valid solution. So let me write the array sorted, the example array sorted. And the trick with sorting is that after sorting, if we know that there is a majority element that appears more than the half of the size in that array, so in other words, the element that takes more than the half of the size of the array, like in this example, however we position that element, its value will be present in the middle of the array. So because it takes more than the half of the array, even if it is positioned at the end or at the beginning, it will still go beyond the middle element in the array. And with this observation after sorting, we can just return the element which is in the middle of the array. So we can just return element of n, nums of n over 2. And that's the entire solution. The complexity of this solution is, the time complexity is n log n, because we have to do sorting, and the space complexity is O of 1. We are not using any extra memory, but the downside, as I've already mentioned, is that we are modifying the input array. And that's the solution with sorting. The best solution for this algorithm is given by the Boyers-Moore voting algorithm. The algorithm has a time complexity of O of n, so we just go through the array once, and also a space complexity is very good, is O of 1. And this is the optimal solution. The algorithm is quite tricky to explain, so I will do my best to explain how it works. We will be maintaining 2 variables. It's not a map, it's just 2 variables. I will write them in a table to track the values, but this is not a map again. These are just 2 variables. The first we will call num, and the second we will call count. The num is often called a candidate because it's a voting algorithm, but we will use num in this example. And we start from the values 0, 0. So it's given, we start that algorithm always assigning 0, 0 to both count and the number. And we will be processing the entire array, so looping through entire array. Let's call that our index is I. And for each loop iteration, we will be doing the following two steps. So the step number 1 will be to check if the count is 0 equals 0. If it is, then we will change the num. So num will become nums of I, so the current element. And then we will do the second step inside the loop, which is the following. We will check if num equals nums of I. Then we will increment the counter, so counter plus plus. Else, if it's not equal, we will decrement the counter. Minus, minus. And let's go through the entire array and show how the algorithm works on this example. So we start from the first element. The element is 1, and we do the first check. Is the count 0? Yes, it is. So we are going to change our num. So num will become the current element, which is 1. And then we do the step 2, and we check, is the num equals the current element? Yes, it is, because we just changed it. So we will increment the counter. And then we will move to the next element. Next element is again 1. So we will do the two steps again. Is count equals 0? No, it is not. Is num equals the current element? Yes, it is. So we will increment the counter. Counter will become 2, but the num will remain unchanged. It's still 1. We will move to the next element. Next element is 2. We will again do those two steps. So is count equal 0? No, it is not. Is num equal the current element? The current element is 2. The num is 1. So it is not. So we will decrement the counter. So the counter will become 1, but the num remain unchanged. We move to the next element and we repeat the process. So is count 0? No. Is num equal nums of I? No, it is not. So we will decrement the count. The count will become 0, but the num remains unchanged. We move to the right. Now we have another 2. So the count is now 0, so we will change the num. The num will become 2, and we will do the step number 2. Is num equal the current element? Yes, it is. So we will say count equals 1, and we will move to the next element, which is 1, and repeat the process. So is the count 0? No, it is not. Is num equal the current element? No, it is not. So we will decrement the counter, but the num remains unchanged. And we finally reached the last element. Is the count 0? Yes. So we are going to change the num. Num becomes 1. And we check, is num equal the current element? Yes, it is. So we will increment the counter. And since we reached the end of the array, this is our final result. And the value we return from that algorithm is simply num. And this works because, as you notice, we have 4 1s and 3 2s, and array is of size 7. So 4 is more than half of the size of the array, and that's why we will be returning 1. This is a very clever algorithm, and it may require you to think about it for a few minutes. And that's the optimal algorithm for this problem. Let's write code for our brute force solution first. So I will start from storing the size of the array. Let's also compute our threshold. And now we will write 2 for loops, 2 nested for loops to process the array. And in the first loop, let's store the current element. And let's initialize the counter. And now we will write a second loop when we will be counting through the entire array, and what we will be counting is how many times the current element appears in the array. So if the current element nums of j is equal our current element, then we will increment the counter. And after we count all the elements in the inner loop, we will check whether that element appears more than our threshold times. And this is the entire algorithm, but to avoid the compilation error, we have to return something, and I will return -1. We should never reach this line because we are being given information that there will always be a majority element in our nums, so should never execute. And that's the entire brute force algorithm. Let's try to build it. It builds correctly, and now let's try to run the tests, and all tests are passing, so we have successfully coded the brute force algorithm for this problem. Let's write the solution for the algorithm that uses hash map. So we will use unordered map in C++. And the solution is as follows. First, we have to define the map. So the map will have a key integer and a value will also be integer, and it will be a number and the frequency. And next, let's compute our threshold. And now we have to process all the elements in the array and add them to the map. And while doing that, we will be checking if we reach the threshold. So let's add to the map first. In C++, when we are referencing a non-existing element in unordered map for the first time, it's gonna be initialized to 0 using this specific notation. So this line will basically either increment an existing value in the map for the num, or it will initialize it with 0, adding the num to the map, and then it's gonna be incremented, so it will start from 1. And now we have to check whether our counter is greater than the threshold. And if it is, we just can return the number. And as before, to avoid compilation errors, we have to return something. So we will return -1. And this line should never execute because we are given a promise that the data will always contain majority element, in which case we will return from the line 15. And that's the entire algorithm that uses unordered map. Let's try to build it. It builds correctly, and now let's try to execute our tests. And the tests have passed, so we successfully coded the algorithm version that uses unordered map. Let's now write a solution that uses sort. So we have to include algorithms module. And this is the shortest solution for this problem. We will use standard sort. And we will sort the entire array from the beginning to the end. And now that the array is sorted, we just need to return the element in the middle. And that's the entire solution. So let's try to build it. It builds correctly. And let's try to see if the tests are passing. And all tests are passing. So we successfully coded a solution that uses sort. And let's write a code for the optimal Boyers-Moore algorithm solution. So we will start from the two variables. As we explained, we will have num and count, the two variables which will be used in the algorithm. And now we have to process the entire array one by one and performs the steps needed by the algorithm. First, we need to check if the count is 0. And if it is 0, then we have to change the number. And then we have to do the second step. In the next step, we have to check if the current element x equals num. So let's do it. And in this case, we will increment the count. Otherwise, we will decrement the count. And after we process all the elements, we just return the num. And that's the entire algorithm. Let's try to build it. And let's see if the tests are passing. And all tests are passing. So we have successfully coded optimal Boyers-Moore algorithm. As a final step, let's verify that all our algorithms are passing LeetCode tests. So we are starting from the brute force solution. And let's try to submit this one. It was accepted, so let's try to actually submit this. And it worked, but the performance is really bad. So let's try the next algorithm. This was the hash map. Let me copy it. And let's see if this algorithm works. It works, so let's try to submit and see if we get any better performance. Yeah, and performance is now much better. So let's try our third algorithm that was based on sorting. Let me copy this one. Let's see if it works. It works. Let's submit it. It works again, and it's passing all the LeetCode tests. So the last remaining one is the Boyers-Moore algorithm. Let me copy this and let's see if it works. And let's try to submit. And the algorithm works and it has a good performance. So we have tested all our implementation and they are all good. This is the end of this solution. The source code is available in the GitHub repo shown on the screen.